Thank you everyone for attending. My name is Michel, and today we're going to go over SQL metaprogramming. And the initial thing we want to start out by saying is SQL code bases tend to accumulate structural debt, and that is because, unlike Python, Python is a language where there's one and only one way to do things. That's part of the Zen of Python. However, in SQL, there are multiple ways to do exactly the same thing. So for example, in the first row, you can see that you can either write a table as a CTE or as a subquery. And this is sort of an organizational difference. There's no one right way to do things. And even when there is one right way to do things, like in the second example, where you can see someone cast a value to 0 if it's a null, there's actually a much easier function to do so that not a lot of people might know about. And even in the third example, the example you see on the left is a very traditional sort of applying a window function and then filtering out the results, top song by artist. This is a very common use case for that. However, there is actually a function that simplifies your life and does it all in one go that not a lot of SQL developers know about. And one of the problems with maintaining SQL is that essentially, if the output is right, you're not really going to care how you got to the output, specifically with SQL, with SQL, because the language itself is simple and you tend not to really think about how you write it. You just care about the report output at the end. So that really tends to accumulate code smells, sort of anti-patterns. And especially once you start to have SQL code bases that are, 10, 20, 30, 40,000 lines of code long, this becomes a little bit of a nightmare to manage. So the central question we want to answer today is, how can SQL code quality and correctness be maintained at scale? And we're going to go over an initial example and sort of to motivate why we would want to do metaprogramming. And the definition of metaprogramming is programs that process other programs. So usually you write a program that gets a value or takes in user input. In this scenario, we're writing programs that will read other programs. And the initial motivating example is this very, very common data pipeline anti-pattern. It's not actually ideal to write pipelines in this manner, but many, many people tend to do this. I've been at multiple companies where this pattern was applied. And in this specific example, we see an initial source table A, and then we have two intermediary tables, B and C, that derive from A, and these could be different granularity levels, different group bys. And finally, in the output, we join them in table D. And there is in this pipeline, due to, developer laziness or due to sort of we made a change and did not take it out, there is a redundant orphan table at the end called E. So for 5 tables, this is pretty easy to put in as a mental model in your head because it's only 5 tables. But I have personally seen this pattern applied to pipelines that are several thousand lines of code long. And that essentially becomes a nightmare to map out by hand. So you need something to draw the dependency graph and see that table A is the source for B and C, which is the source for D, and that E is an orphan, and you can even automate the removal of E. But to even get to that level, you first need to create this graph. So a question here, what is your first instinct as an engineer when you look at this script and you want to create a graph where the nodes are the tables and the edges are the dependency of one table on another? If you look at the script, what's the first tool that comes to mind to do this? A hint, it will involve some sort of text manipulation. How do we extract table A, table B? How do we extract the joins out of this script? What's your first instinct? Exactly, regular expressions. So the first instinct that you would have to analyze text is usually to use regular expressions. And for those of you who are unfamiliar with regular expressions, it's basically a mini language, what we call a DSL, a domain-specific language, because it's not general purpose. It's built only for the domain of processing text. In fact, just describing textual patterns. That is literally the only purpose for this language. So we're not going to go over the language itself. This is a sort of very standard tool in the toolkit. I will just briefly explain how it works. You basically have symbols that represent certain a digit or a word or a character, and you can specify, if you look at the second line here, if you want 1 or 2 or more, and you can even specify how much of each character that you want. And this language essentially describes patterns of text. If you want a concrete example, you can look here, and if you look at the text, you see order 42 cost $1299, and let's say we want to find all of the numbers in this piece of text, we would write this regex. We want to capture any series of digits. So, and if you want to apply this to our specific SQL query, this specific regex script, and I can zoom in here if you want to see it, this will capture, if you look at the output, this will capture any word that comes after either a from clause or a join clause. So hypothetically, this should give me all of the tables that a certain query depends on, and you can see the output in this case is A and B. So this is regex, and regex is very well studied. It's a well-known tool. And if we want to apply regex to the specific example we listed at the start, it would look something along these lines. So we first want to have two regex patterns. The first one is the temporary table capturing regex. And this will capture the actual table itself, the node in the dependency graph. The second one is one that captures the dependency, the edges. So this will capture any table that comes after from or join. And if we look at the output, or if we look at the query here, we can see the example we set out at the start. And we will simply, all that we will do is simply process it line by line, and then try to see if that line captures either the creation regex or the from join regex. And that will essentially allow us to create the dependency graph and represent it as a UML, represent it in U4J. The point is we actually now have this graph, and you can see here that E is an orphan, and E can be essentially eliminated. So the practicality of building these types of graphs, or even the practicality and the usefulness of inspecting your SQL code and optimizing it via code, metaprogramming SQL, is apparent. However, I just want to ask you, is this particularly readable? If you're looking at the script and you encounter this, I would start to swear, I think. This is not readable. This does not tell me what I'm capturing. Regex is infamously very, very not readable. So actually, if you really want to build the correct, robust capture statement, because a from statement in SQL can have aliases, it can have spaces, it can have new lines, there can be a subquery in it, the cases are almost infinite. And to actually build a robust pattern capture for from, it looks something along these lines. And this is monstrous, this is a nightmare. I do not want to have to read this or maintain it. I cannot debug this if I want to debug this, right? So regex does work, but it has many different pitfalls. Unreadability is probably the biggest one. One of them also is that it is essentially read-only. So it's a domain-specific language built for matching patterns of text. That is the only purpose it is built for. It does not handle transformations, so it can only capture. Another one is that it is fragile to formatting. And as we just discussed, new lines, aliases, if you use backquotes to put in a column name, that you will need to account for all of these different cases in the regex capture string itself. And finally, and probably the most important pitfall aside from unreadability, is that regex does not know that it's editing or capturing pieces of an SQL query. It doesn't know. It's a blind tool for text pattern matching. It is not a tool for SQL code inspection. It can be used for that, but it is not the primary purpose of it. So if we have a generic tool, probably we can find something that's specific that might be more applicable to us for this particular use case. And I just want to reference one last thing about the pitfalls of regex. I'm not sure if you know this infamous Stack Overflow answer. This is like 15, 16 years ago, where someone wanted to create a pattern matcher for HTML. And they basically built a regex string. You can look at it here, where it essentially sort of captures A tags, and they did not want it to capture other tags. And they asked, is regex the right approach? Is this the right string? And this is one of the most infamous answers on Stack Overflow. The guy starts out by stating the reasons why, and then you sort of see a steady descent into insanity as he sort of tries to explain more and more that, this is not the tool for the job. Don't use regex when you have parsers that are built for that. So again, regex will work, but you will hate your life while you're attempting to do the solution in regex. And here there was a little bit of a spoiler for the actual solution that we're going to go with, which is parsers and ASTs. So an AST is a fancy word that simply means how the compiler and how the machine will actually run the code at the end. Because as you know, in the end, all computation, you can reduce it down to 2 inputs and a logic gate and an output and some combination of the above. I'm oversimplifying, but that's basically what you can do. In the end, it's all logic gates. 2 inputs and an output looks like a binary tree. So theoretically, at some point, your code is going to be translated to some sort of tree. And the AST is actually how that structure is represented. So if you have this Python code, x is equal to a plus b divided by 2, the actual way in which it will be executed is it will start at the bottom level. It will add a plus b. It will get the result of that, give it to the division operator, which will divide it by 2. And then it will go to the root level and then assign this value to x. And this is basically, ASTs are the eventual fate of all programs. All programs get converted to ASTs. In fact, the job of the parser is to take the code as input and to output the AST. And every language will have its own parser. Many languages have several parsers. The idea, we don't really care about the specifics of each parser. All that we want is to take a query in and output a tree. Once we output a tree, we just have a tree. And the tree is a very well-known data structure. And we can apply all of the classic tree algorithms that you learned in university, from DFS to BFS to islands to net. All of these, you can apply them to SQL and actually get meaningful results. So let's look at an example of a AST. So this is sort of a generic query. We don't specifically care about what it says, but I just want you to see how it's actually represented in the output. And of course, in Python, we will store this as a JSON, as a dictionary, because we can nest as many things as we want. We will simply import sqloxide. There are other options as well. I just used sqloxide because it outputs a sort of very simple JSON dictionary that we can sort of inspect. But if you want to look at the output on the right-hand side, you can see that initially we have a with. So this is a common table expression. And that is basically represented in the query, in the dictionary. And actually, in the dictionary, what we find is that the key represents some semantic concept in SQL, whether it's a clause, a filter, whatever, an alias. And the value is either some nested structure or the thing itself. And I'm just going to give you an example. The alias for this common table expression is t. So with t as select x from y, we can look at the alias and find it in this particular part of the dictionary. What do you think would happen if I mutate this t and I call it f? What would happen to the original query? If I change the value of t here to x, k, y, what would happen to the original query if I translated it back? It would change, basically. The with t here would become with x, with k, with y. So what is the idea here? We change the query into a JSON, to a dictionary. We modify the dictionary, and then we return it back as a query, and that will allow us to basically ad hoc change SQL queries. We're writing a Python script that is taking a JSON representing an SQL query and either just inspecting it or modifying it and returning it back as a new query. And the AST is always one-to-one with the code. So you can rely basically that one code always has one AST representation and vice versa. So this is the output. And if you even want to look later on below, you can see that here we have select x from y. This is an unnamed expression because we did not put in a alias. And if you even scroll down below, I'm just going to show you some other things as well. Here, for example, if we have a group by function, we have an identifier. This will basically give us the function that we're using. And even here, you can already imagine the applications of this. You can change functions, change variables, change columns completely ad hoc. Completely ad hoc. It's simply a modification of a dictionary. Yes, go ahead. So, yes, so basically, if we scroll down below, there should be a from. Here it is. So basically, the key is always either like a semantic concept in SQL or the clause itself, so a from or a select or whatever. And the values within it will give you the tables, the joins, etc., etc. So what I usually do is I obviously don't memorize the structure, so I just output whatever I want. I just look at how I want to modify it and then target that small part of the JSON. I'm actually going to show an example at the end. Obviously, this is not meant for human consumption, so it's not. You're not meant to read the entire thing. You're meant to read the parts you want to change or the parts you want to inspect and work only on those. So you can basically ignore the majority of the tree and just target the thing you actually want to inspect in it. But this is where it would be stored. There's a specific from key that's in the query itself.
Right. So if you modify the with t,
yeah.
then it gets updated.
Yes. It won't get updated here automatically here because you will need to do it manually, not manually, with the script. It's not reactive, if that's what you're asking, but it's quite easy to just modify it with the script itself twice. But it's not reactive, no. Any other questions? So actually, let's go back to the initial example and redo it with ASTs. And the primary difference is that you no longer have these weird regex strings that are essentially unreadable. You actually have something that is aware that we're working with tables and is aware that we are working with dependencies of tables. So we actually now look at the key, that's the table key, whether it's in the actual dictionary itself, and then we start to build these edges in a way that, again, is SQL aware. So here we're not building some generic regex. We are actually getting a key representing the create statement, for example, in SQL, or the from, or the where, the having, the whatever. So the most important part of this is we are now working at one level of abstraction higher than we previously were. We are no longer working with a generic matching tool, but we have access to each and every clause in the query, and we can actually manipulate them, use them, and so on. So I want to go through several small examples of how you can actually use this practically speaking, even starting tomorrow, right? One very common anti-pattern in SQL is you have a nested subquery and a nested subquery and a nested subquery and a nested subquery. Usually you don't need to do this. 99.9% of the time, you maximum need a subquery depth of maybe 3. 99.9% of the time. And usually, especially when you're a little bit more junior, you sort of want to show off that you know how to use recursive subqueries, and you usually want to put something in the CI/CD pipeline to say this subquery depth is greater than X. Don't, or at least review it, lint it, whatever. And to note that I have not at least found any SQL linters that do this. So that's why I sort of initially wanted to explore that as well. So if the SQL query is a tree, how do we get the depth of a tree? DFS, depth first search. This is tree algorithms 101. The first algorithm you learn on a binary tree is probably DFS. All that we're doing here is using DFS to calculate the depth of the subqueries that are nested within. And you can see this is literally just like a standard algorithm. And we can see here that if we try to run it on a query that is 1 layer nested, it returns 2. But if it's 2 layer nested, it returns 3. And literally all that we're doing here is whenever we see a select, we see if there's a select recursively that's nested within it, and we're just adding +1s. That is literally the entire algorithm. And you can just write this as a script in your CI/CD pipeline, throwing up a warning if it's greater than some X. So this is one example with what you can actually do now that you have a mental model of SQL queries as trees. The other one is auto-aliasing aggregates, meaning, I do this as well. When I'm lazy and I just have an aggregate function, I will just do something like select sum from A. I will not name it. Many other people use this as well. It's sort of developer laziness on our behalf. And what we want to try to do is to see, is there a way to reasonably, automatically, auto-alias all of this? For example, sum of A gets transformed to total underscore A. Some sort of automatic transformation that happens on these aggregates. So before we look at the actual algorithm, we first want to inspect, and this I think goes back to your question, it's a big tree, right? How do I find the from, how do I modify the t's and so on? What I tend to do, at least for this example, is I want to look at the sum of A, and I want to see how is that represented in the AST. So what I did here was I wrote the query, I parsed it, I took the select. This part just takes whatever is in the select. And this is the JSON output. This is the dictionary output. And you can already immediately spot unnamed expression. So this is an unaliased expression, sum of A. There's something there that we haven't given a name to. And you can see within the function itself, you see a list with the identifier. You even see the arguments that pass into the sum function, and so on. So we know what we want to target. We know what we want to match. And what we want to match is an unaliased aggregate expression. So we also want to see what is the end result that we want, and we essentially work backwards from it to transform the thing on the left to the thing on the right. And what we find is the exact same query, when we add as total underscore A to it, when we add an alias to it, it looks different. It looks like this. The key is expression with alias. That's an immediate change we see. And then we see that for the most part, it's relatively speaking the same. All that we're doing at the end is just adding an alias key with the actual value, which is total A. So actually what we know we want to do is transform this structure to that structure. And if we want to add the alias, we will add it as the value of this key, alias.value. So now we have this transformation planned out in our minds. How do we actually execute it? How do we actually write code that does this? So it would look something along these lines. What I first started out by doing was an alias map. So if we have a sum, we prefix it with total. If we have average, we prefix it with mean. If we have count, we prefix it with n, etc., etc. This is just to make it a little bit more interesting. As an example, we can even map it. We can have custom logic built on top of it. And then with this function, I isolate, if you remember the key I was just talking about, the alias that has the actual name of the aggregate function. So this part is isolated there. And then basically what I do is, if you find an unnamed expression, get whatever is happening in that unnamed expression, map it to the alias map, see what function is actually there, and then return exactly the same expression, except you're adding an alias. So all that we did was, if we go back, we transformed that structure, preserving the exact computation. We transformed it into that structure. That's all that this function does. And we can see the result immediately. Select sum of revenue, average of price, count of orders. This will basically, if you notice, there are no aliases here, but the output is, select sum of revenue as total underscore revenue, average price as mean underscore price, and count of orders as n underscore orders. So basically, this removes all of the hard work for us, right? If the tree algorithm itself is airtight, if the logic is sound, and if your transformation is sound, this work can entirely be automated. So this is another example in which you can actually use the tree structure to do transformations en masse, right? Like you can basically safely run this on your code base and relatively speaking, be confident that 99% of the time it's going to work. And one other example I want to give, which is also quite similar to this, is wrapping denominators in NULLIF. And this is sort of also another classic sort of initial SQL error. If you have select sum of A divided by sum of B, if it turns out to be 0, the SQL query is going to bug out. So how do we automatically identify every single denominator in our entire code base and just wrap it in a NULLIF? No matter what the expression in the denominator is. This could be a single column, this could be a function, this could be a subquery, this could be a whatever. As long as it's in a denominator, I need to wrap it in a NULLIF. So how do I actually do this? The process is quite similar to what we did before, which is basically I start out by isolating the specific structure in the AST that represents the NULLIF function. So when I did this, I found that this is the structure. Function, identifier, the value is NULLIF because that's what signifies what the function is. And then basically, in the arguments here, the arguments this is basically a list. The first value in the list is the first argument. The second value in the list is the second argument. And I basically know that I don't really need to care about the second argument. I want it to be 0. All that I want to edit is the first argument of this function. So I need to edit this exact position in the schema. That's all I need to touch. I need to touch nothing else. Literally, all that I need to do is take whatever was in the denominator and paste it here. That's it. And the other thing we actually also need to know is, well, how are division operators actually represented also in the AST itself? And this is actually expressed as something called binary op, because it's a left and right operation. It will take the left value, which is the numerator, as x. The operation is divide. And by the way, even looking at this, you can already conclude you can arbitrarily change divide to like multiply, whatever, this is all, your SQL query is data that you can edit, is basically the takeaway of all of this. But actually what we want to modify is the right key here, which is the denominator, because we know here that when we wrote select x divided by y, and we parsed it, we got that value as the denominator. So the actual application of this would be something, again, very, very similar to what we did with the auto-aliasing. It's just a different sort of shift. If we have a binary operation and that binary operation is a divide, we will simply copy whatever is there and just wrap it in the NULLIF expression that we saw. Just put that expression in the list that we saw here before as the first element in this list, in the args list. That's all we did. We copied that, we pasted it there, we mutated or transformed the original AST. And if you look at the example, select A divided by B and X divided by Y minus Z, we can see that it will basically capture both cases. So it is robust to whatever is in the denominator. If you have a correlated subquery, if you have a whatever in the denominator, it will capture it. So this will eliminate one bug forever from your code base, forever. You should never find a division by zero error in your code base again, just by running this, ever. So this is also very useful for defensive programming, essentially. And one last sort of quick example, just to also show that there are so many applications of this. In fact, there are infinite applications of this. The mental model is your SQL is data that you can edit and data that you can manipulate. That is the takeaway from this talk. And here, for example, let's say we have a very long query. We want to find unused common table expressions because sometimes I might write a long query. I might forget that I set a common table expression somewhere. And I want to automatically identify candidates for elimination. So if you look at the unused CTE's sort of example query, we have with select with A as select A, with B as select B, with C as select blah, blah, blah. In the end, it tells me that C is not used because it's defined once and referenced nowhere. And how did we actually do this? Also a very similar process. This is basically a graph algorithm. I will build the edges out. If I find an orphan that is not being referenced, if I find a leaf node that's not being referenced anywhere, that is what I will return. And also, just to end with a couple of other examples, usually if you have two queries with the same granularity level, so group by year city, group by also year city, but like with a different expression on top, usually you can combine the queries because same granularity queries, you can refactor whatever's in the where clause, you can refactor whatever's in the select to accommodate both of the queries. You can just write a AST, a function that uses the SQL ASTs to find all queries and group all queries that have the same granularity level. And you can even write code that auto-transforms them, auto-merges them. So the applications are essentially only limited by your own imagination. Start to think of SQL queries not just as queries, not just as code, but as data that you can manipulate. And I will end on two small FAQs. The first question is, this seems like a headache. Why would I not just use an agent to do all of this? And there are actually many reasons why you would not want to use an agent. First of all, a deterministic process is always more reliable by definition than a probabilistic one. LLMs are not deterministic. The second one is token costs. I think enough said. The third one is, especially with large language models, LLMs tend to hallucinate quite often. And actually something I found is LLMs tend to use a lot of cross joins, even though 99% of the time, no one uses, it's very, very rare to use cross joins. But they tend to be overrepresented in the code that that LLMs output, and that is essentially because they're overrepresented in the training data, which are essentially SQL tutorials. But the middle ground here is to use the LLM to write the three algorithms. So you don't need to do the difficult work of the parsing. The last one is Python the best suited language for this? Probably not. You can get by with Python. The thing is that at some point you have to start thinking of code as data and data as code. This is actually what homoiconic languages do. Usually Lisps, you also have Haskell, Julia also, they do all of this. Python will work, but you will probably start hating yourself if you sort of take this all the way to production with it. But the main takeaway is your SQL queries are also data. And thank you.